So, like the way we did the two phase representation for a two channel filter bank, we will look at we will look into the M channel filter bank and derive a polyphase representation for this, and it will be very useful from our understanding to see how the structure of polyphase fits in to the analysis and synthesis filter banks. Okay, so from our previous discussions, by polyphase representation, we can write Hk of Z summation as summation L equals 0 to m minus 1 Z power minus L E k L of Z power m, and this is the type 1 representation. So, we will look into the type 1 representation, polyphase representation for analysis filters, right. I choose some kth analysis filter, right. So, some k equals 0, 1, 2, so on till m minus 1. I will choose one such k in the analysis bank, and for that analysis filter indexed by k, I have an m phase representation, right, L equals 0 to m minus 1. That is the whole idea about this notation. Now, we can write the representation, polyphase representation in matrix form for a stack of all analysis filters, right. We stack all the analysis filters H naught of Z so on till H m minus 1 of Z, and we link this with the polyphase components and then the delays, right. So, we can write the delay also, that becomes easier for us to see through. 1, there is no delay, unit delay dot 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 till m minus 1 delays, right. So, H naught will have E naught naught of Z power m. You multiply E naught naught Z power m with 1, E naught 1 Z power m with this delay, so on and so forth, so on and so forth. It is just a different way of writing things. When you stack all the analysis filters as a column vector, you can write this in matrix form. So, you have dot 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 here E 0 m minus 1 of Z power m, so on. This is E m minus 1 0 Z power m dot 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 E m minus 1 m minus 1 of Z power m. And I call this matrix as some bold E of Z power m, having all the polyphase components, and this is basically a vector of delay elements, and this is basically a stack of all the analysis filters, right. And you can see that in matrix form h of z is E of z power m times E of z. Okay. So, this is writing it in matrix form. Similarly, we can do this for the synthesis filters. And for this purpose, we will look into the type 2 polyphase representation. Okay. So, we have this form. So, now our stack of filters f naught of z so on till f minus 1 m minus 1 f m minus 1 of z can be written in terms of the delay vector and the polyphase components, type 2 polyphase components. At this point you may be even wondering why I need type 1 here and type 2, type 1 in the analysis and type 2 polyphase representation in the synthesis, but things will become very clear in a short while why we need this this form of representation. Okay. So, I think if we are set with this matrix equation, we can write this in this form in a compact way. F transpose of z is basically z power minus of m minus 1 times some e tilde of z is vector times r of z power m. Right, and this e tilde is this transposed version of your E of z, right, and I would just mark them here. This is E tilde of z, I pull the z power minus m minus 1 outside times E tilde of z. So, it is z power minus of m minus 1 times E tilde of z, where E tilde of z is E of z transpose. Okay. And this is our R of z power m, and this is F transpose of c. So, before we end with this slide, a small set of corrections. The matrices are typically in bold. So, this R matrix has to be in bold following our notation. Similarly, something here, and this transpose is actually transposed a little bit off. So, we can have this transpose just here. Okay. So, with this what we do is we take the analysis bank and write this in polyphase form. So, this E of z power m is basically a matrix which has all these polyphase components, and then we provide delayed inputs to this bank of polyphase components, right. This is one and the same. So, this representation is basically the architecture schematic, sort of schematic for this matrix equation. So, this is the analysis bank. Similarly, we can do this for the synthesis bank. So, let us just focus on the synthesis filters. F naught of z. So, you have all these band signals coming in and they are going through these synthesis filters. M minus 1 of these. And this is equivalent to having all these band signals that go through a type 2 polyphase decomposition followed by delay elements that combine the outputs. Now, we are not yet complete because we have to introduce our downsamplers and upsamplers, right. So, let us go one step further. Now, we have this input going through these, that goes through these delay lines. We have E of z power m, which is our analysis filters in polyphase form. We have downsamplers in each of the branches. Then we have upsamplers. Followed by synthesis filters in type 2 representation. and our reconstructed signal. Now, this is not enough for us because it is difficult to analyze how the polyphase filters E of z power m and R of z power m, how the polyphase filters behave, right. I mean, it is impossible to look at the spectrum and then analyze if we can get perfect reconstruction property or not through the analysis of the schematic shown in this architecture here. I will call this as architecture 1. With just architecture 1, it is impossible for us to study any properties on perfect reconstruction. But we will apply a familiar trick that we have learned, which is through Nobel identities. We will push these downsamplers before this bank and we will push these upsamplers after this synthesis bank. So, the trick would be apply Nobel identities to simplify architecture 1 further towards analysis on perfect reconstruction properties. So, I think once we realized that we have to apply Nobel identities, it is probably straightforward. So, with x of n, we bring in these downsamplers here, there is a delay followed by downsampler within this branch, and this would now be E of z, not E of z power m. And we have our R of z, this bank, we have upsamplers, followed by delay elements, and then we combine the signal to get x hat of n, and this is architecture 2. I want to make this distinction very carefully here, that this is bold E and bold R, indicating that they are matrices. Now, you have to ponder a little bit why architecture 2 is useful for us. Now, if we say that our overall transfer function P of z, not overall, but I combine E of z and R of z to some transfer function P of z, right, and if P of z is an identity then this is like our delay filter bank. You see this, if P of z is identity, we are left with a delay filter bank, and we know that the delay filter bank is perfect reconstructing, and your intuition should tell you that out after m minus 1 delays you should get your reconstructed output, because we saw the example for a 2 channel bank and we got it after a unit delay. So, after m minus 1 delays you should get your reconstructed signal, right. So, therefore, this P of z plays a very important role here, but P of z need not be identity, right. We may not land up with an identity. How should we design our analysis and synthesis filters such that P of z is some delay? So, these are questions that one can ask, and aside, one has to note that if Hk of z is causal, causality is also very important here, then Ek of z is also causal. And then we may have to choose R of z. I will mention this as a goal. Choose R of z to meet the design specs. And what is our design spec? It should be alias free, it should satisfy perfect reconstruction property, etc., right, and maybe some specifications of the distortion as well. So, this is a very useful representation, and that is the reason why we introduced type 1 and type 2, because if you did not do type 2 representation in the synthesis side, you would land up with difficulties, because you could not get the upsamplers. I mean, the delay elements would not be symmetric here. I mean, you would have to introduce delays in the middle here. So, imagine that you followed exactly type 1 for synthesis, you will have to have delay elements here immediately, and that would be hard to even think about how that would have an impact, because you have delayed versions of the subband signals followed by filtering and upsamplers and all that. It would be very messy to analyze such systems. So, this is very elegant, it is symmetric, because you have 2 delay elements, 2 chain of delay elements on either side, followed by upsamplers and downsamplers on this side, and then the bank of filters. So, there is a lot of symmetry, in architecture too. So, therefore, this is useful for our analysis as well. Okay. So, we will stop here and then we will delve little bit deeper into the properties for perfect reconstruction for M channel filter banks, and we will see how polyphase design, polyphase representation can help us overcome some of the issues with stability, etc., if we were slightly clever in the way we design these filters. Okay. So, with this we complete this module, we can stop here.